These are the notes for AP Calculus on the topic of volume using the disk method and volume using the shell method. So with the disk method, when you're finding the volume, you're basically using a circular disk. Oops, change the color here. And the thickness of that disk is dx. So we start with the area of a circle, which is pi r squared, where r is the radius. And I'm going to call it R1 here. And then when you multiply that by the thickness dx, it's like a really short cylinder turned on its side. That's what gives us the volume of that disk. However, sometimes what we have is when we're taking a region or revolving around axis, sometimes it's not a solid disk like this. Sometimes there's a hole in that disk. And if there is, then we have to subtract the volume of that hole. So that's what I call R2, the radius of the hole. So if we take the volume of the outer disk and then subtract the volume of the hole, which is the inner disk, that'll give us the volume of the material here. So since we're integrating, we're going to integrate all these infinitely thin disks. So pi times the outer radius squared, it's going to change depending on the x value squared, times dx minus pi r sub 2 squared times dx. That's the volume of the inner disk. And then we can pull out the pi, because that's a constant out in front. And then integrate. This is going to be the x coordinates where the region starts and stops. And then you're just left with the outer radius squared minus the inner radius squared, if there is a need for that, if there is a hole. So let's see how this works on a without calculator problem. So let's sketch the graph. So you can either set equations equal to each other to see where they intersect, or in this case, you can just plot some points. So let's graph each of these here. So x equals 4. That's a vertical line. Right here. And then y equals 0. That's just our horizontal line right on the x-axis. And then we can graph the square root graph. Plug in some simple points. You can substitute in 0, square root of 0 is 0. Substitute in 1, square root of 1 is 1, so it goes to the point 1, 1. And if you substitute in 4, the square root of 4 is 2, so it goes to the point 4, 2. So by plotting some points, you can figure out your region enclosed is right here. Bounded means enclosed by. So it says set up the interval to find the volume revolved about the given axis of revolution. So in this case, our axis of revolution is the x-axis, which is one of our boundaries. So you can indicate the axis of revolution by a little circular arrow there. And then we can draw a representative rectangle in there. And we're also going to go over the shell method here in just a little bit. So the way you can easily tell which of these two methods to use is there's a little mnemonic device. Here we've got this. This represents half of one of those disks. It's going to revolve around this. So in your rectangle, your representative rectangle and your axis of revolution, notice they're perpendicular here. So for the disk method, if your axis of revolution, which oftentimes we'll draw as a dotted line, If in this case it was just the x-axis though, and then our rectangle dx. Notice here they're perpendicular, so a little mnemonic device, you can remember perpendicular. That's when you use the disk method. And that's what we have right here. Rectangle and x revolution are perpendicular, so we use the disk method. And then R1, the outer radius, always goes from the axis of revolution, because that's where the center of our figure is, to the far end of the rectangle, which could be the top or the bottom, depending on which one is further away. So in this one, R1, here's our axis of revolution, goes from there to the far end of the rectangle. And whenever you want a vertical distance, you do the top minus the bottom. In this case, the top, whoops, I forgot to label this graph here. This is the graph of y equals the square root of x. So that's the one on the top of R1, square root of x, minus, on the bottom is just 0. So R2, notice when we revolve around this, see how there's not going to be any hole in this. It's going to be a completely solid shape. R2 would normally go from the axis of revolution to the near end of the rectangle. But in this case, you can see there is no gap from the axis to the near end of the rectangle. It's just 0. So you can either say R2 here equals 0, or you can basically say it's not needed. We'll see other problems where there is a hole we have to subtract, but here we don't. So then to set up our integral to find the volume, we have pi on the outside. Integral, the region, using the x coordinates, everything's in terms of x. The region starts at x equals 0 right here, and it stops at x equals 4 because of that vertical line, stops our region. And then you just have R1 squared, which is square root of x squared, and then times dx, that's what turns it into volume there. If there was an R2, you'd have to also subtract R2 squared. And so this we're going to do without a calculator. So pi, let's just simplify this first. Square root of x squared is just x. And then when you integrate x, using the power rule, you add 1 to the exponent x squared over 2. That's why I did from 0 to 4. And when you plug in 4, you get 16 divided by 2 is 8 times pi. Minus, when you plug in 0, it's just 0. And it's just volume, there's just general units here, so it'd be units cubed. That'd be the volume of that three-dimensional shape. Taking this region, revolving around the x-axis. All right, now let's take a look at the shell method without a calculator first. So the way to remember is the shell method is when your axis of revolution and your rectangle are parallel or parashell. So we have a rectangle like this. And our axis of revolution is parallel to it. So folding around something like that. You can remember para, or parallel, but remember parashell. So that's when we use the shell method. Because the wording of these questions look very similar. So it's all based on how the rectangle and axis of revolution, if they're parallel, shell method, if they're perpendicular, disk method. Otherwise, these problems could be worded pretty much identically. So on the shell method, it really just comes from, we've got a cylindrical shell. It comes from the formula for the surface area of the part that wraps around. It's like a paper towel roll or a toilet paper roll here. And where both the top and bottom are open. And then it's got some thickness to it, which is what turns it into volume. That's dx. So we just use the surface area formula for a cylinder. The part that wraps around, remember, is the circumference, 2 pi r times the height, h. So that's what we have to integrate, just all those. Now here, because they're open when you revolve around, these you don't have to subtract anything because there's already a hole. They're all already hollow. And then we multiply by dx, the thickness, that's what turns it into volume instead of just surface area. So here we can pull the 2 pi out in front, and p of x represents the radius, and h of x represents the height. Those would be the two things we need to figure out instead of r1 and r2. So this is find the volume of the solid revolution by revolving the region bounded by these about the y-axis using the shell method. So one method, you can plug in points like we did here to see what the region enclosed looks like, or the other method you can use without your calculator is to actually set the equations equal to each other. So that's what I'll do on this one. Set negative x squared plus 6x equal to 0. And then solve that. In this case, you can factor out a negative x as a GCF. And then what you're left with is x minus 6 equals 0. So we can see the x coordinates of our points of intersection are x equals 0 and x equals 6. And then notice the y coordinate's got to be 0 because one of our equations is y equals 0 here. So we can graph that one first. Oops. There's y equals 0. And then we know it intersects at x equals 0 and x equals 6. Those are our two x-intercepts. And you can plug in some more points too if you want. We just need to see where the region starts and stops here. Or if you just recognize, notice this is a parabola. The highest exponent is 2. It's got a negative, so it's a parabola that opens down. And we know it crosses through these 2 points. So the vertex would have to be, because of the symmetry of a parabola, right smack in the middle at 3. If you plug in 3 real quick, you can get negative 9 plus 18 gives you 9. And then you can sketch the graph. We just need a rough sketch, really, to get what the region enclosed is. Okay, so there's our region enclosed. But this time we're revolving it about the y-axis. So this is our axis of revolution right here. So we'll draw a representative rectangle. And that's dx again. And notice our rectangle and axis revolution are parallel. That's why we're using the shell method here, as opposed to the last one where they're perpendicular. And then this part is optional, but it's to help you visualize the radius and the height here. So we're taking this rectangle and it's revolving around here. So it's going to form this, what's called a cylindrical shell, like a hollow cylinder. So I'll use the color there, because it really comes from this rectangle. So this represents one of those cylindrical shells. And then we have an infinite number of different ones of different heights here. And by adding up the volumes of all of those, that's what's going to give you the volume of this whole three-dimensional shape there. So the two things we need are the radius and the height. So you can see the radius, p of x, goes from the axis of revolution to our rectangle. And when you have a horizontal distance like this, remember you do the right minus the left. And wherever your rectangle, wherever you draw the rectangle is, this is some point xy. So that just represents the x coordinate. It could be anywhere where you drew the rectangle. So it'd just be x minus our axis of revolution here is the y-axis, which is x equals 0. So it'd be x minus 0. And anytime you're revolving around the y-axis, that's what the radius is going to be. We'll see some other ones where it's not just the y-axis, where it's a little modified. But it always has the x in it from where your rectangle is, because that's always x away from the y-axis. And then the height, h of x, you can see right here, that's the height of our cylinder. It's really the exact same thing we would use if we were doing the area of this region, just the top minus the bottom of the rectangle. So on the top of the rectangle, we've got this graph, which I forgot to label here, is y equals negative x squared plus 6x. That's our parabola. So it'd be negative x squared plus 6x minus the one on the bottom. In this case, it won't always be, but in this case, it's 0. That's on the bottom of a rectangle. So when we set up this integral, we'd have 2 pi on the outside with a shell method instead of just pi. Then the integral, the region starts at 0 and stops at 6. That's why we set them equal to each other to figure out where they intersect. And then you just have the radius, p of x, which is x, times the height, h of x, which is negative x squared plus 6x, all times dx. Because this gives you the surface area of the cylindrical shell. Remember, it's open on the top and bottom. And then when you multiply by the dx of thickness, that's again what turns it into volume. So here we just have to multiply this out, so it's easier to integrate. So x times negative x squared would be negative x cubed. X times 6x, 6x squared. And now since they're added here, you can just integrate each one separately. So you've got 2 pi on the outside. And when you integrate negative x cubed, you get negative x to the 4th over 4 plus 6x cubed over 3. I went from 0 to 6. You can see this one simplifies a little bit. 6 divided by 3 is just 2. So we'll have 2 pi on the outside. And then when you plug in 6, we've got negative 6 to the 4th over 4 plus 2 times 6 cubed. And then it's just a matter of simplifying that. So I'll just move, I'm running out of room here, so I'll just move the simplifying part right up in this space right here. So we've got 2 pi on the outside. And then what you can do to make it easier so you don't have to figure out 6 to the 4th, notice this has 6 cubed, this has 6 to the 4th. So you can actually take out the 6 cubed as a GCF. Make our calculations a little easier. And then notice what's left is there's 1 6 left, so negative 6 over 4 reduces to negative 3 halves, and then plus 2. That's all that's left of that term. Well, 2 is 4 halves. So then we just have 2 pi. 6 to the 3rd power is 216. And then negative 3 halves plus 2, which is 4 halves, is 1 half. And then notice the 2's reduce out here. So all that's left is 216 pi. It's 216 pi, and again, it's volume, so it'd be units cubed. So that's the volume of that. Taking this region and revolving around the y-axis, that three-dimensional shape. All right, so now let's take a look at some with the calculator. And these will be mixed up on whether you use the disk method or the shell method. All right, so let's start off with the I already have the axis revolution drawn in here. You can see it's y equals negative 2 is right down here. I drew his dotted line, so we're going to revolve around that. And this one has 3 different boundaries. So let's go ahead and enter these. I'll start off with 84 in our calculator here. So when there's a negative on the front, use the negative in parentheses. And then natural log x. And then notice the 7 is not inside the natural log, so close parentheses, then plus 7. And then we've got 2, and then to the power. And since this 0.6x is all in the exponent, you do have to put an open parentheses. Otherwise, it will only raise the 2 to the 0.6, and it won't realize the x is also an exponent. So 0.6, or you can just put 0.6x, close parentheses. And then x equals 1, that's a vertical line. So that one our calculator will not graph. It's not a function, but we can just graph it on paper. There's no need for the calculator to graph it. And then the window size, you just have to play around with it so you can see the region enclosed. In this case, though, to zoom in on the region, I set up the x and y axis on paper here, so it's a little easier. So I'll go from -1 to 6 on x min and max, and -2 to 9 on the y min and max, and then graph it. Remember, it's going to graph them in the order we type them in. Okay, so there's the graph of the first one, and then the graph of the second one. So it just has to be a rough sketch here. So the graph of our natural log one, something like that. And so it's y equals negative natural log of x plus 7. And then our exponential one looks something like that. It's y equals 0 to the. So even though your calculator is graphing for you, always graph it on paper as well. Make sure you set it up correctly. And then we've got our vertical line, which our calculator won't graph. So we can just put that on paper. It's just a vertical line, x equals 1. Oops. Like that. So now you can see the region enclosed right in here. So then we can draw a representative rectangle. With dx. And now we can see which method to use. Notice here's our rectangle, here's our axis of revolution. They're perpendicular, so perpendicular. So this would be the disk method. So that means we need R1 and R2. So for R1, remember it goes from the axis of revolution to the far end of the rectangle. So here's our axis of revolution to the far end of the rectangle, which in this case is the top. Let's write down what that would be. Because that's the outer radius. When we take this region and revolve it around the line y equals -2 down there. So it's the top minus the bottom. The one on the top is negative natural log of x plus 7. And then minus the one on the bottom here, I'll just label it. This is y equals -2. So minus -2. Which becomes plus 2. And then for R2, in this case, there is a gap between our axis of revolution and the region. So if there is an R2, it goes from the axis of revolution to the close end of the rectangle, which in this case is the bottom. There's a radius of the hole that we have to subtract. So R2 is going to be the top minus the bottom. So the one on the top for R2 is 2 to the 0.6x. Minus the one on the bottom, -2. So notice they're both plus 2. And you're going to see that pattern with the disk method. If there is an R2, R1 and R2 will look similar to each other. So when we set up our integral here, notice we can see the region starts at 1, but we need to figure out where it stops. So I'll just call this A. So let's go ahead and set up the integral, and then we'll see how we can figure this out and work it out on our calculator. So since it's the disk method, we'll have pi on the outside. The integral is going to be from 1 to a, and we'll figure out what a is. And then it's r1 squared. So we have to square them separately, so it'll be negative natural log of x plus 7 plus 2 squared. Now I know you could make that plus 9, but it'll actually be easier to type in our calculator if we don't. Minus, we'll have 2 to the 0.6x plus 2 squared. And then the whole thing times dx. So make sure you set up your integral correctly. And then we'll use our calculator to figure out what that is. So let's see how we do this on our calculator. So first I'll enter this in for the Inspire, then we'll have our find our point of intersection on both of them. So for the Inspire, a new document, add graphs, and the negative out in front, negative. Natural log here is control and then ln of x, and then the plus 7 there, and then hit the down arrow to F2 is 2, then hit the exponent button, and then 0.6x. Here you don't need the parentheses because it already puts it up, the whole thing up in the exponent. Whoops. 6x. Enter. And then you can change your window size, menu, window zoom, window settings. So let's change it the same we did for the 84. So we'll go from -1 to 6, x min and max, and y min -2 to 9. Okay, and again, we don't need to graph the x equals 1. We did that on paper, our calculator. That's not a function, we'll do that. So let's go ahead and find our point of intersection using both calculators. Go back to the 84. So remember for the 84, you go second calc, number 5, intersect. And then first curve, y1, there's only 2 in there, enter. Second curve, y2, hit enter. And then guess, just move your cursor, either type into guess or move it closer to that one. Hit enter a third time. And we get, make sure you're accurate to at least the thousandth place, so 4.134. So don't forget to write it on paper, otherwise only you and your calculator will know what it is. So we'll put A equals 4.134. But then we don't want to type that number in, and we want it to the full accuracy. So the way we store it in our calculator, we go second quit, store, and then alpha A. Now it's in there for A. And then on the Inspire, you just go menu, analyze graph, and then intersection. Lower bound, just move the dotted line to the left of it. Upper bound, move it to the right of the point of intersection, and then there it is. Highlight, we just want the x coordinate. Hit the var button, store, and then hit A and enter. All right, now all that's left is to enter this integral in our calculator right here. So let's start with 84. So you don't forget the pi. Let's do that first. Second pi. And then math number 9. So this is what the older ones look like. Some of the newer ones will look more like what you have on paper here. So you just have to put things in different ways. On the older ones, you have to first put what you're integrating. So you have to first put parentheses, open parentheses for this light blue one here. And then this, I don't have to type in like this because I have it in as y1. So I can just go vars, y variables, y1, and then plus 2, close parentheses, squared, minus another open parentheses. This I have to type in, it's already in there for y2. So vars, the right are y variables, number 1 function, y2, and plus 2, close parentheses, squared. Again, on the newer ones, you don't need commas, but on older ones like this, you need a comma and then x. On the newer ones, you put this x right next to the d at the very end. And then on the older ones, comma, you put the lower limit 1, and comma, the upper limit alpha a. On the newer ones, you just put these right where it looks like on the calculator for upper and lower limits. And you get 380.786. And be accurate to at least the thousandth place. Again, it's volume, so it's units cubed. All right, let's see how we do this on the Inspire now. So for the Inspire, just go doc, insert calculator. And this is going to look kind of like the newer 84s in terms of the format. You just hit pi first, which is on this button. And then the integral is right next to the 9 here, the def integral. So the newer 84s look like this. You put 1 there, you put a right there, and then here's going to be the x, and then we put what we're integrating here. So you can again just put open parentheses, and we put the first negative natural log of x plus 7 is f1, so var f1 of x. Oops, I forgot the open parentheses here first. So open parentheses, 1 of x plus 2, that's squared, minus another open parentheses, var f2, that was our exponential one, to the 0.6x of x plus 2 squared. And thus we get the same thing, 380.786. Let me just change my settings so I get a little more accuracy. It's accurate enough on this one, but sometimes it may not be. So we'll go menu, dock, settings. So if it doesn't give you enough accuracy, you guys just got to change this. I'm going to change it to float 12 so it's a little more accurate, and make default. That's a little more accurate on the next one. All right, let's take a look at the next problem now. Whoops. Sorry about that. There we go. Also, with calculator. This one you could do without calculator, but we're going to use the calculator on it to make our integral a little easier. So let's go ahead and enter these in here. So y equals, I'm going to clear these out. And the first one is just 3 minus x squared. Whoops. And for y1, 3 minus x squared. And for y2, x plus 1. And window size, let's change it from -7 to 2 on our x minimax. And let's go -2 to 4 on the y minimax. And graph those. Oops, I think I made the window size a little off here. Oops, I put -72. To 2 here. Let's try that again. All right. So here's the graph of the first one, parabola, and there's our linear one. So let's sketch this on paper. So our parabola looks something like this. It's 3 minus x squared. And our linear graph, you can see it's but 1, it has a slope of 1. Something like this. Just a rough sketch again. Doesn't have to be perfect. Just enough to help you see the region enclosed. So y equals x plus 1. And this time our axis of revolution is x equals -3. Again, draw it as dotted just so it doesn't get mixed up with the region enclosed there. So there's x equals -3. All right, so the region enclosed is right in here. And if you draw your representative rectangle, and you can put it anywhere in this region just to make it a little easier to see why it works here, though. I'm going to put it in the first quadrant instead of in the second and third here. Still works in the other ones, just a little easier to see how to set it up correctly. So notice in this case that rectangle and x origin are parallel, so this one's going to be the shell method. And we need the radius and the height. So this represents one of those cylindrical shells. Again, this is just to help you visualize the radius and the height. So the radius, p of x, would go from x revolution to the rectangle. Again, wherever you have your rectangle here, this is x, y. So you do the right minus the left. So this is x. On the previous one, it was revolved around the y-axis that we did the shell method. So it's x minus 0. But in this case, it's going to be x minus, right minus left. The left is at negative 3. Which you can see simplifies to just be x plus 3. Another way to see why that makes sense, you can see this little distance here from the rectangle back to the y-axis, that represents the x-coordinate. And this distance here is 3 from the y-axis to this line. So see how you did x minus negative 3? That gives you x plus 3. That will give you your total radius. And then the height, again, is just the height of your rectangle. Becomes the height. It's the same exact thing you would use for area. So h of x would just be the top minus the bottom. So 3 minus x squared minus the one on the bottom is x plus 1. And you could simplify that, but since we're doing it without, with calculator, we don't need to. All right, so now let's figure out our region starts and stops. Let's find the points of intersection here on our calculator. So I'll start with 84. Second calc intersect. First curve, just y1. Second curve, y2. You can guess over here. And notice in this case, it's exactly negative 2. That's why we could have done this without our calculator by setting these equal to each other to figure out where they intersect. So when it's just negative 2, we don't really need to store that as a. And same thing on the other one. Second calc intersect. First curve enter, second curve enter. I'm going to guess. You can just type in a guess. I'm going to guess this one's at 1. Hit enter. And it is exactly at 1. So again, we don't need to store that. Our calculator is B. So since it's the shell method, we'd have 2 pi on the outside. Integral from negative 2 to 1. And then we just have p of x, which is x plus 3, times h of x, which is 3 minus x squared. And again, even though you could simplify, I'm not going to because it's easier to type in your calculator this way if you don't, because these are already in our calculator. All times dx. So I forgot to draw it here. All right. So let's go ahead and enter this in our calculator here. So I can quit. So this time we have 2 pi on the outside. And math number 9, function integrate. So this time we're integrating open parentheses x plus 3. And then times, open parentheses, this one was y1. So vars, y variables, y1 minus x plus 1, that's y2. So vars, y variables, y2. Close parentheses on that. And then comma, our variables x, comma, the lower limit's negative 2, comma, the upper limit's 1. So we get 70.686 units cubed. And let's just see how to do this on Inspire real quick. So Inspire, I'll just close this up here. Document, graph, so the first one is 3 minus x squared, x plus 1. There's our region. And again, when you do the points of intersection, lower bound, upper bound, you get negative 2 there. Analyze graph, intersection, lower bound, upper bound, you get 1. So again, there's no need to store them. And then just go doc, insert calculator. and 2 pi on the outside. Integral from -2 to 1. Again, this is what the newer 84s look like also. And then parentheses, x plus 3. The only thing you have to be careful of in Inspire, especially if the p of x is just x, sometimes you actually have to put the times here instead of just putting the parentheses next to each other. Otherwise, it might not understand that you're trying to multiply. It might think you're creating a new function, especially when it's x. And then, so it's f1 of x minus f2 of x dx. We get the same thing. All right, let's take a look at a couple more, also with calculator. All right. So here we've just got 2 equations here. Let's go ahead and enter these in. We've got 3, and then arctangent, remember on the calculator, that's the same as second, it looks like tangent with a -1, x, and then notice the plus 5 is not inside there, so close parentheses, plus 5. And then y2 is just x squared. And then let's change our window size. Let's go -3 to 5 on x min and max. And we'll go -1 to 11 on the y min and max. Just to zoom in on our region. And then graph it. So there's the graph of the arctangent. And then there's the graph of our parabola x squared. So let's just do a quick sketch of that. So there's a rough sketch of our f of x. And g of x. Again, not a great graph, but that's okay. We don't need it to be to set it up correctly. And then we've got our axis of revolution this time is y equals 11. That was a dotted line so we don't mix it up with a region enclosed there. Y equals 11, and that's what we're revolving around. So let's draw a representative rectangle in there. Dx. And again, look at our rectangle and the axis of revolution. Notice they're perpendicular, so perpendicular. So this would be the disk method. R1, remember this region is going to revolve around this axis, goes from the axis of revolution, right here, to the far end of the rectangle, which in this case is the bottom. So R1. In this case, on the top of R1 is our axis of revolution 11, minus on the bottom is g of x. It'll be 11 minus g of x. And then this one does need an R2 because there is a gap between the axis and our region. So it goes from the axis of revolution to the close end of the rectangle. That's the radius of the hole. So R2, again, on the top of R2 would be 11, minus on the bottom is f of x. And then we notice in this case need to find our 2 points of intersection. In this case, it won't work out as nicely here. So I'll just call them A and B. So we'll write them down and store them in our calculator next. So second calc, intersect, first curve, 1 second curve y2. I'm going to guess this one's at -1, so I'll just type in -1 as my guess. And it's -1.449, so let's write that down. And then let's store it in our calculator as well. So second quit, store alpha A. And let's find the other one, second calc intersect. First curve enter, second curve enter. Let's guess this one is at 3. It's at 2.955. And let's store that in our calculator. So I can quit, store alpha b. All right, now let's go ahead and set up our integral. Again, it's the disk method. So we can have pi on the outside. It's an integral from a to b. And then it's just r1 squared minus g of x squared minus r2 squared, 11 minus f of x squared all times dx. And let's go ahead and enter that in our calculator. So we have pi on the x side, second pi, and then math number 9, function integrate, and then we're integrating, in this case, open parentheses for the orange one here. 11 minus g of x, that was our y2, so vars y variables y2, close parentheses squared, they got to be squared separately, minus, open parentheses here, 11 minus f of x, that was our y1, so vars y variables y1, close parentheses and square that one. And then the older ones you have to put comma x, comma lower limit alpha a, comma upper limit alpha b. So we get 761.302. And its volume, so it's units cubed. All right. There's nothing really new on the Inspire on this one, so if you have questions on it, just let me know. But otherwise, you pretty much do the same type of things we did on the other ones here. So I'm just going to show on 84 for these ones, these last two. And so we got one last one. So let's go ahead and enter in these two equations. Clear these out. So we've got x to the power, and then if you have an older one like mine, you have to put in parentheses, so it knows that whole 2/3 is the exponent, and then we've got 2 sine of x plus 1. Okay. And then let's change our window size. Let's go -1 to 12 on x minimax, and -1 to 7 on the y minimax. Oops, scale, keep that 1. Graph it. So there's the graph of our f of x, x to the 2/3. And there's our sine graph. So you can see the region is right in here, that little region close. The rest of the sign doesn't matter. So we'll just graph this real quick. That's the only part of f of x that matters. Form our region. And then the only part of sine that matters is this part right here. There's g of x. All right, so this time we're going to revolve it around x equals 5. Right over here. And then we draw a representative rectangle in here. You can draw either anywhere in here, but first quadrant's a little easier to see why it works. Notice our axis of revolution here. And the rectangle are parallel, so para shell. So this one is the shell method. So if we draw our cylindrical shell in there so we can visualize the radius and the height a little more easily, look something like this. So our radius, p of x, would be from here to here. That's the radius of the cylinder. So notice again, wherever your rectangle is just x. So the one on the right would be 5 minus the one on the left is x. Another way you can see that, you can see this distance from here to here. That's x. That's the x-coordinate from there to there. And the distance from the y-axis to the line is 5. Let's see if we go 5 minus x, that gives us what the radius is. But again, if you just do the right minus the left, that'll always give you the correct radius. And then the height, h of x, it's just the top minus the bottom. So in this case, on the top, just like we do for area, the top one is our g of x, minus the one on the bottom is f of x. And then with the shell method, we'll have 2 pi on the outside. And then we just define our points of intersection. Again, I'll call them A and B. So let's use our calculator to figure out what those are, and we'll write them down on paper and store them. So for A, second calc intersect, first curve enter, second curve enter. I'm going to guess this one's at -1. It's negative 0.626. Let's store that in our calculator. So quit, store alpha A. And let's find the other one, second calc intersect. First curve enter, second curve enter. I'll guess this one's at 2. It's at 1.447. So let's store that in our calculator. So quit, store alpha B. All right, so now we're all set there. Let's finish setting up our integral. And again, it's just the radius for the shell method, p of x, which we figured out is 5 minus x, times the height, which we figured out is g of x minus f of x. Again, always make sure you write down your integral correctly, as most of the points on both my test and the AP test are for setting things up correctly. And then all times dx. All right, let's just enter this in our calculator and see what our answer is. Again, there's nothing new on the Inspire here really, so I'm just going to show it on 84. So we've got 2 pi, math number 9, and then we need parentheses 5 minus x. And Inspire, you might need to put a times here, but here, otherwise you can just put open parentheses, then g of x, that was our y2, bars y2 minus f of x, that was our y1, so bars y variables y1, close parentheses, and then comma, x is our variable, comma, lower limit is alpha a, comma, upper limit is alpha b. Sometimes it takes a little longer, so 58.769. And it's volume, so units cubed. And that concludes the notes for AP Calculus on the topics of the disk method and the shell method.